ready to start. So you're very warmly welcome to the second event of our distinguished lecture series in future information technology. So we had our first event in just before Christmas with something like 150 participants. And now we are, I think, closer to 200, so we have a really nice growth in the participation. So, of course, hope that we keep on the nice trend. So, if you look at our kind of next events in this series, we have quite nice presentations coming up from Turing Award winner Leslie Valiant and Knut Prize winner Christos Papadimitriou. So we are hoping that we will get you there as well. Okay, but today I have the pleasure to introduce Dr. Eric Brown from IBM. So Eric is the director and principal investigator for Watson technologies at the IBM Watson Research Center. Eric earned his Bachelor of Science at the University of Vermont and Master of Science and PhD at the University of Massachusetts, all in computer science. Eric joined IBM in 1995 and has conducted research in information retrieval, document categorization, text analysis, question answering, bioinformatics, and applications of automatic speech recognition. Since 2007, Eric has been a technical lead on the DeepQA project at IBM and the application of automatic open domain question answering to build the Watson question answering system. Okay, so the goal of Watson is to achieve human-level question answering performance, and this goal was realized in February 2011 when this Watson system beat two human experts in this Jeopardy quiz show in television. Okay, so without further ado, I give the floor to Eric, who will tell everything about the Watson system. So, please.
Well, I can't tell you everything about it, but I'll tell you as much as I can. So thank you and good afternoon. It's really a pleasure to be here to talk to you about Watson. And first, let me start by saying that actually in 2011, IBM celebrated our 100th anniversary. And so in the field of information technology, for a company to be around for 100 years is really quite remarkable. And especially when you look back at IBM's origins, we started by making some of the world's best meat and cheese slicers for delis. But actually there's a very interesting history of innovation at IBM over the years. We quickly moved into things like tabulating machines and punch card machines, which were essential for some of the early big accounting tasks, especially in the United States when they wanted to take the census and then support things like Social Security. These technologies were essential. And then moving forward, IBM built the first commercially viable business computer with the System 360. IBM invented things like the Fortran programming language, which has been essential for a lot of scientific computing. We invented the relational database in 1970. We actually invented the reduced instruction set computer, the RISC processor, which is really, I think, the foundation of most modern microprocessors these days. And so after such a rich history of innovation, when it comes time to celebrate your 100th anniversary, I think the obvious thing to do is to build a computer that can compete on a television quiz show. And so that's what we did. So actually that's not entirely so obvious. And what I'd like to do is tell you enough about it so that you can agree that this is actually a very interesting challenge. And by achieving that goal, we've actually built some technology that has very interesting business applications. And I'll specifically talk about how this technology is being applied in the healthcare space and trying to solve medical diagnosis problems. But let me start with a little bit of background. The basic problem we're trying to solve is to provide humans with information to help them make better decisions. And what you see here is the traditional model of how we go about leveraging tools to help us make decisions. So you have a question, and you need to find information for answering that question. You know, what do people here do if they need to go search for something? What might you use? You can yell it out. Google. Well, I didn't necessarily want any name brands, but let's say you're going to go use web search. And so for web search, you can take your 2.5 keywords on average, and the search engine will be more than happy to find 10 or perhaps 10 million web pages that are relevant to those keywords. But now, all you get back are the links to the documents. And so now to actually make your decision, you're still responsible for drilling down into that information and reading it, assessing it, whether or not it's really relevant for the problem you're trying to solve, and then ultimately going on from there. And what we want to do is really shift the burden from the decision maker onto the tools and give users more powerful ways to find and leverage relevant information. And so here's the really where we're trying to go, where now instead of a search engine, you really have more of an expert who can understand a natural language question, can understand all of the resources that are available to answer that question, pick out exactly what's relevant, perhaps assess its relevance for you and come up with some confidence in that information, and then give it back to you so that you can more easily digest it and make your decision. Now, it turns out that this model is not new, and in fact, librarians have been serving this role for decades, if not centuries. The problem with human librarians, though, is that they don't scale. Either we no longer have expert human librarians available to us, or I think more importantly, human librarians can't have as deep a knowledge of the huge, vast resources that we'd like to leverage to help us make these decisions. So we need to automate this expert on the right-hand side. And the technology for doing that is called open domain automatic question answering. And this has actually been an area of research for several decades. You can go back to 1970 and find an article in the Communications of the ACM that is a summary of the state of the art in question answering technology. So now I'm looking at the audience, and I think I see a lot of students here, most of you who were probably not even born before 1970. So just think about 1970, a survey article on the state of the art of this technology. That's over 40 years ago. And yet, as of, let's say, 2005, this was still a very interesting and challenging problem. In fact, I'll argue that there are aspects of it today that are still interesting and challenging, so we continue to work on it. The basic task of such a system is, given some rich natural language expressed over some broad open domain, we want it to return us precise answers with accurate confidences, consumable justifications, and ultimately a fast response time. So these are all sort of the requirements of the technology. Now, as I said, we've been working on this for a while, and in fact, even at IBM, had been exploring question answering technology since the late 90s into the early 2000s, but the results that we had been producing had sort of plateaued, and that was with a relatively modest investment. We had still produced some arguably state-of-the-art technology, but we're really looking for a way to really improve the performance, because at that time, it still was not at a level that you could really apply commercially to solve real problems. So at IBM, when we want to explore some interesting, challenging scientific problem, we like to elevate them to something we call a grand challenge problem. And grand challenge problems have a few key characteristics. So first, it should be something that can capture the imagination of a broad audience. And if you look to one of the other more recent grand challenges that IBM has taken on, you can see that in Deep Blue, the computer system that we built to play chess. So back in the early 90s, building computer systems that could play chess was an interesting problem in artificial intelligence. And in fact, at that time, a lot of people didn't believe you could build a computer system that could play at the level of a human grand champion. And in 1997, I believe, IBM demonstrated Deep Blue against Garry Kasparov and showed that, in fact, you can build a champion-level computer chess playing system. The second aspect of a grand challenge problem is the need to engage the scientific community. So again, I work in the research division at IBM, which is about 3,500 scientists worldwide. And so we're interested in driving important scientific advances. And then the third element for IBM is to work on technologies that will ultimately be relevant to our client problems and solve some interesting business applications. So this is the nature of a grand challenge problem. And now let's just briefly compare the chess grand challenge problem with something more in the natural language space. So now if you think about it, chess actually, while a hard problem in the 90s to solve, ultimately is this fairly well-defined mathematical problem. Building a computer system that can play chess ends up being fairly straightforward in terms of representing the game, the possible moves. Granted, there's an enormous search space and a lot of computation required to solve that problem, but ultimately it's explicit and it's unambiguous. Now let's compare that with natural language, and in particular search or question answering. Understanding human language is a challenge. Now, as humans, it's actually very easy for us to communicate naturally, rapidly, and in fact, when we do communicate, we leave a lot unsaid. There's a lot of communication that's implicit, and we don't even realize how ambiguous language is. There's so many different ways to say the same thing, and a particular saying or phrase can actually have different meanings depending on the context. And so ultimately, natural language is based on context and grounded in this human cognition. So it's quite a bit different from chess as a grand challenge problem. And let me make that a little more clear with an example and sort of compare and contrast what we expect computers to be able to do well versus what might be more of a challenge. So first, let's take a look at this equation here. The natural log of 12,546,798 times pi squared divided by 34,567.46 equals, anyone? So for the human brain, that is actually fairly hard to compute, but something that you would easily do with just a calculator, possibly one even built into your watch. So very trivial. So when we're dealing with numbers and equations, we expect computers, even simple ones, to be very good at dealing with those algebraic expressions, maybe not so much for humans. Similarly, if we have information that is structured and represented with explicit semantics, these tend to be straightforward for computers again. If we wanted to know what David Jones's payment was for his laptop, if we've used, let's say, relational technology to create these different tables of information where the columns have explicit semantic types, we would expect a computer to easily navigate through these tables. So assuming we were searching for David Jones, it would match character by character to find David Jones in the owner table, and then easily navigate to find the payment. Again, the information is explicit, it's structured, computers should be able to deal with that. However, as soon as we get even a little more creative and we search with Dave Jones, our simple matching algorithm of going character by character breaks down. Now, Dave is a very common nickname for David, so as humans we would expect this to match, but if the computer program is not smart enough to understand that heuristic, we run into a problem. And so again, just going from structured information into strings and not even getting into real natural language starts to pose a problem. That gets us to Jeopardy as a way to drive and demonstrate this technology. So it turns out that Jeopardy has 5 key dimensions to it that make it a really interesting and challenging problem for question answering and natural language understanding. The first is this broad open domain. So if you're not familiar with Jeopardy, it's this very popular quiz show on American television where there's this board of questions and 3 human contestants. They will pick a question from the board. The text of that question is revealed. The host will read the clue, and then the humans have to come up with an answer and ring in and get to respond. But the topics cover an enormous variety of areas, from ancient history to science to popular entertainment. And so, in fact, here are 5 real Jeopardy clues just as an example. So for $200, the juice of this bog fruit is sometimes used to treat urinary tract infections. Does anyone here know that? Cranberry. That is correct. And now, if you've ever seen Jeopardy, there's a little subtlety there, which is when you respond to one of these clues, you have to respond in the form of a question. So the correct response technically would be, what is cranberry? For $400, this world capital on the Gulf of Finland boasts a railway station designed by Elio Saarinen. I'm sure everybody here knows the answer to this one. Again, real Jeopardy clues, randomly selected. Just pulled these right out. For $600 in cell division, mitosis splits the nucleus and cytokinesis splits this liquid, cushioning the nucleus. Any biologists in the audience? We're looking for cytoplasm here. For $800, Grace Murray Hopper is credited with applying this 3-letter term to a mysterious computer problem. What is a bug? I hope you're not a software engineer here. Came back with that answer very quickly. And then finally, for $1,000, most modern supercomputers run on this operating system developed by Linus Torvalds. Again, I would expect everybody here to know that one. Clearly, we're talking about Linux. And so, again, 5 real Jeopardy clues, but representing a broad range of topics over things from home remedies to actual biology questions to computer terminology to geography questions here. So you can see there's a number of different things that Jeopardy could ask about. So if we're going to build a computer system that can actually respond to these questions, we have to think in very broad, generic terms about how we're going to solve that problem. The second aspect is complex language. You can see just from these clues that they're expressed using rich, complex language that takes some time to understand even as a human. And so imagine writing a computer system that can analyze and parse these things. The third element is the need for high precision. So here, again, is the difference between search and question answering. In Jeopardy, it's not sufficient to just do a web search and return a hit list of web pages that might contain the answer, even if you're confident that that top-ranked hit contains the answer somewhere. You have to drill down into the text and pull out that specific entity, that phrase, cranberries, Linux, Helsinki. And so precision, getting to the precise answer, is important. The fourth dimension is the need for accurate confidence. And this is important because in Jeopardy, when you get the clue correct, the value of the clue is added to your score, but when you get the clue wrong, the value of the clue is subtracted from your score. So you're penalized for answering incorrectly. And that means you have to not only come up with the correct answer, but an estimate in your confidence in that answer so you know whether or not you want to risk attempting to answer it. And this is a very important aspect of the technology, because in real applications of question answering, or more generally decision support capabilities, decision support systems, you want to have an estimate from your information system of how accurate that information is, because if you make bad decisions with the wrong information, you're going to get penalized. And then the fifth element of this Jeopardy challenge is speed. The system has to come up with its answer and its confidence in, on average, about 3 seconds, which, for a business application is important. A lot of the research and question answering prior to this had been done in a more academic setting where the focus was on make it work. And we never quite got to that point of now make it work fast. And here, that is a key element. And so it really kind of combines all of the important aspects of the challenge together. And again, it's all about natural language and how we understand it and interpret it. So let me give you just one more, well, I have a few more examples, but here's the next example. So this clue comes from the category Lincoln blogs, and so it's US-centric, so a little bit of background. It's a reference to Abraham Lincoln. He's I think he's the 16th president of the United States, one of the more famous ones. And Lincoln Blogs is sort of a wordplay on Lincoln Logs, which is a popular children's toy. But the clue here is Treasury Secretary Chase just submitted this to me for the third time. Guess what, pal? This time I'm accepting it. Anybody want to hazard a guess as to what we're talking about? Resignation. Excellent. So either you're familiar with U.S. history, particularly around the Civil War era, and you just knew that Chase had submitted his resignation 3 times before it was accepted. Or perhaps you're just a little more cynical about politics and you imagine what could a secretary submit to their president. It could be a bill, it could be a speech, most likely it's their resignation. You look at the words submitted and accepted, and that's the connection that you make. Now, I was presenting Watson to some middle school students, so these are students in the 6th grade, so let's see, that's going to be like ages 11, 12, 13, and gave him this clue and didn't really expect anybody to know it because it's a little esoteric, it's a little subtle, but one girl raised her hand, and so I called on her, and her response to this clue was, "What is a friend request?" And so now bear in mind that Lincoln was president in, the mid-1800s. And so I thought, well, I guess if Lincoln did have Facebook back in 1860, he may very well have been friends with Secretary Chase. But what really struck me about this was, why would a middle school student come up with that answer? It's because they see the words submitted and accepted and associate that with Facebook. I mean, clearly we're talking about a friend request. And, more generally, it has implications for how you interpret language and its meaning. It's all very contextual. It's how is it most commonly used. And in fact, its meaning and context can change over time. And so, again, another lesson about the challenges of dealing with natural language. So let me give you a few more examples. So in May 1898, Portugal celebrated the 400th anniversary of this explorer's arrival in India. Does anybody have any guesses on this one? I think I heard the correct answer, Vasco da Gama. In the U.S., people will often answer Columbus or Magellan. Those are perhaps the only explorers we know of. But, of course, Vasco da Gama would be the correct answer here. And now, how would Watson go about solving this? First, Watson is going to analyze the question and break it down into individual keywords in that question, possibly parse it to come up with the syntactic structure and break it into sort of subject, verb, object triples. And then we might start by using those keywords to search over all of our relevant content to try and find a passage that contains the correct answer. So now, having searched with those keywords, we might encounter this passage. In May, Gary arrived in India after he celebrated his anniversary in Portugal. So actually, this is a pretty good matching passage. It has celebrated, May, anniversary, Portugal, India. Clearly, Gary is the correct answer, not Vasco da Gama. I'm sorry. Nobody has ever heard of Gary the explorer, so that again is probably not the correct answer, and this is just sort of a made-up example to emphasize that keyword search may lead you astray, and just because you have a good keyword match at the lexical level, the surface level, doesn't necessarily mean you found the right answer. So here's another passage that does contain the correct answer for that question. On the 27th of May, 1498, Vasco da Gama landed in Capet Beach. Here, if we just look at keyword match, we see we have a bit of a problem. There's only a few words in here that actually match. I think that there's of and May. May is a month. It's also an auxiliary verb, and so it typically doesn't have a lot of content associated with it. I think the other matching words are just prepositions, in and of. But when you look at that, it does actually answer the question. But to understand how well it supports Vasco da Gama as the correct answer, we have to do deeper analysis, deeper reasoning over the content here. So we might need to apply something like temporal reasoning to know that if in 1898 we're celebrating the 400th anniversary of something, that something occurred in 1498, and we have a match. Statistical paraphrasing, which is a technique for knowing when two words or phrases can mean the same thing, so that landed in can mean the same thing as arrived in, and we have a match. And perhaps geospatial reasoning to know that Capet Beach is in Kerala, which is in India, and so again there we have a match, but only after doing much deeper analysis. And so this really gets to some of the fundamental approaches that we applied in this Watson question answering system, we needed to bring in a much wider variety of deep analytics to analyze evidence and help us score answers to come up with the best answer. A couple more examples. So from the category common bonds, here you're given 3 words or phrases and you're supposed to come up with the common bond between them. So if I give you shirts, TV remote controls, and telephones, what's most common between those 3 things? Buttons. Although I was giving this presentation to some executives for some big company, and one of them said, "What are things under my couch?" Which, you know, TV, shirts, TV remote control, shirt, telephone, under your couch, sure, arguably correct, but the most popular answer here would be buttons. And so trying to find the connection between these 3 items is the challenge here. Another example of something we call a missing link clue, and this will become important later on when we get into the medical domain, is a clue where there's some piece of information that you need to bring into the analysis, which is not the final answer, but sort of an intermediate step there that then gets you to the final answer. So the clue here is, on hearing of the discovery of George Mallory's body, he told reporters he still thinks he was first. So now, unless you happen to know who George Mallory was, you probably don't know what this is talking about. But if you knew that George Mallory's body was recently found on Mount Everest, at least at the time this clue was given, Mount Everest becomes this missing link, this intermediate piece of information. And so now, if you think about Mount Everest and who thinks he was first, or who claims to be first, that gets you to Sir Edmund Hillary as the correct response to this clue. So a few examples of the kinds of things that we see in Jeopardy. So now when we look at how to measure performance of a system that answers Jeopardy questions, we actually have a way of measuring that, and we can start by measuring human performance. And so what you see here is a graph of human performance on this task, and it turns out humans are pretty good. Each dot on this graph shows the performance of a Jeopardy champion, a human player who won one of these Jeopardy games. Each game consists of about 60 questions, 3 players. So, if they got their fair share, they would each answer about 1/3 of the questions. What you're seeing here is on the x-axis within that game, what percentage of all the questions that winner attempted to answer. And so on average, a Jeopardy champion answers 45 to 55% of the questions. And along the y-axis, their precision. Of the questions they attempted to answer, what percent did they get correct? And again, they have pretty high precision, 85 to 95%. Those red dots represent our equivalent of a grand champion in Jeopardy, Ken Jennings, who is famous for winning 74 straight games in a row. And so when Ken Jennings was playing Jeopardy, he actually answers more like 63, 64% of the questions and gets 92% of them correct. So he knows an awful lot, he knows when he's right, and he wins an awful lot. And again, perfect performance on this would be in the upper right corner where you answer all of the questions and get them all correct. So that's the target performance, or that's a representation of human performance on this task. And as I had mentioned earlier, we'd been working on question answering with a relatively modest investment since the late 90s, and that brown curve along the bottom plots the performance of that legacy system when we first started looking at this problem back in late 2006. And as you can see from that performance is pretty far away from where we would need to be if we were going to have a competitive Jeopardy system, something that could compete against humans. So that was the gap that we needed to bridge, and because of that gap, we felt that this was worthy of a grand challenge problem, and we gave ourselves 3 to 5 years to try and bridge that gap and solve the problem. So how do we go about doing that? Let me give you a little more detail on the Watson technology, and then talk about how we apply this to different applications. So first, we started with what I'll call some early philosophical commitments. And the first one is that large handcrafted models are not going to work. So what do I mean by that? If you look at different approaches to artificial intelligence in general, but more specifically, let's say, knowledge representation and reasoning, there's been a lot of effort to create fairly rich, formal, and complete models of knowledge. It turns out that this approach tends to be fairly brittle. When the knowledge base covers the problem domain and you're asking questions or trying to reason within that domain, they can be quite powerful and give you very precise results. But as soon as you step outside that domain, they start to break down. And what we wanted to focus on were techniques that could scale across broader domains. And so we were going to avoid trying to handcraft things, use human knowledge engineering to try and solve this problem, and instead leverage as-is knowledge resources. And so what do I mean by that? Well, specifically, it's knowledge the way humans naturally communicate it and record it, which would be text. So here, the big focus is on leveraging text resources or unstructured information. And that's ultimately going to rely on a variety of natural language processing techniques and different analytics. So this is where the second point comes in, this intelligence from the combination of many. We want to use a variety of techniques to generate a number of candidate answers or hypotheses. And then we want to apply a wide variety of analytics to find evidence that can support or refute those hypotheses, and then drill down and deeply evaluate that evidence. So I showed you a couple of examples of the kinds of analytics I'm talking about with the statistical paraphrasing or the geospatial reasoning. But in general, we want to be able to apply a wide variety of them, which implies an architecture from a software engineering perspective that makes it easy to integrate all of these analytics, and an underlying mechanism for combining the results of all of these analytics, which ultimately was a probabilistic machine learning approach. And I'll talk more about that in a moment. So as I mentioned, we needed this architecture to support the integration and learning. And then the last point here was to drive performance with measurement and analysis. And so this is sort of a comment on the methodology. And we're having some conversations earlier today about how you go about conducting research in these different areas. And it can be very tempting to focus on specific component technologies, things like information extraction, where my task is to identify named entities or relations. And there are communities built up around creating these technologies, which are very important. And there are test sets and metrics for measuring the performance of these systems. But to what extent does a 2 or 3% performance improvement in named entity detection affect the overall performance of my system? I don't know unless I measure end-to-end performance. So the focus is always on end-to-end system performance and guaranteeing or ensuring that what we're building and enhancing actually solves the ultimate problem, which is this question answering problem. So here's the overall architecture that we developed, again, at a very high level. And the processing breaks down into a few main stages of an overall pipeline. So first you can see along the top different knowledge resources that are used in the system. And again, most of these are going to be text resources, unstructured information. In the case of the Jeopardy system, these would be things like Wikipedia, encyclopedic content that's going to cover a wide domain of topics. As we get into more specific business applications of the technology, you can imagine we're going to be using resources that are relevant to that particular domain. So in the medical domain, we're looking at things like medical textbooks or medical journals from the medical literature. So this is all of the content that's put into the system. Now, what does the system do with that? So we start with an input question and some question analysis. So as an example here, there's another clue. Each year, the EU selects capitals of culture. One of the 2010 cities was this Turkish meeting place of cultures. So when that comes into the system, we start by doing question analysis. First thing we do is apply what I'll call our natural language processing stack, a whole series of analytics that break the question down in individual tokens, parse the question, so basically doing sentence diagramming to find the subject, the verb, the object, the different parts of speech, possibly some named entity detection, detection of any relations that are specified in the question, and then identifying what we call the focus of the question. What's that part of the question that, if we were to replace it with the correct answer, would actually make the question a statement? And so, having analyzed this question, Watson will break it down into these individual keywords with this sort of very high-level parse representation, and determine that we're looking for a place, and moreover, the correct type of the answer is going to be a city or a capital or a place. Now, with all of that, it proceeds to the next stage of the pipeline, which is searching over all the content to find candidate answers. And as a result of that candidate answer or hypothesis generation process, we'll then search over the content, over documents, passages. If there may, in addition to documents, we may have some semi-structured resources in there. All of those things can be searched over to generate possible candidate answers. And for our search engines specifically, we actually use Lucene as one of our search engines, and another open source search engine called Indri, which is a collaboration between the University of Massachusetts and Carnegie Mellon University. And then it will generate possible results here, such as Brussels, Essen, Ottawa, Turkey, Sarajevo, Istanbul, etc. So now with those candidate answers, we're going to go into the next stage of the processing, which is now the application of a wide variety of analytics that will find additional evidence to support or refute each of these possible answers as the correct answer to the question, and score those answers and associate essentially a feature for each analytic and answer. All of these features then make their way down the pipeline, and we can actually organize these different features into something we call an evidence profile, which gives an indication of, for each candidate answer, its weight along different dimensions. So we can group these analytics into things that might look at, let's say, geographic information or passage support or perhaps temporal information, and then create a visual representation of the strengths of each of these candidates along those different dimensions. And then finally combine all of those analytic scores into a final score for each candidate answer, rank order them, and return them in that order. And this combination of scores is done using machine learning. So at the end of this processing pipeline, each candidate answer might have 500 different features, basically a real number associated with it. And the question is, how do we weigh and combine all of those features to produce the final score? We do this using a fairly simple logistic regression approach, and with training data that we run through the system can then learn how to weigh each of those features, basically the coefficient in the logistic formula. And then when we run it on new test data, apply those weights to come up with the final scores for the answers. And so in total, there's a combination of natural language processing techniques, information retrieval, knowledge representation and reasoning, deep analytics of the nature that I described, and ultimately machine learning to weigh and combine all of these different analytics. Individual components themselves could be implemented using a statistical or machine learning approach. So there's actually a combination of rule-based and statistical components in there. And then to scale this whole thing out, we use a parallel and distributed computing platform because actually as you work your way down the pipeline, there's this big fan out of data. We start with one question. We may generate several searches, which in turn produces 100 search results, which might generate a total of 300 or 400 candidate answers. Each candidate answer then is evaluated with another 20 or 30 pieces of evidence. So we have several thousand pieces of evidence, and all being run against maybe 100 different analytics. All of this can be done in parallel and independent of each other, and so it's, as we like to say, embarrassingly parallel and easily deployed on a parallel computing environment, which ultimately allows us to address that speed requirement of all of this processing. So the last point that I'll make about the Watson technology is this methodology for rapidly innovating and advancing the technology, which hinged on a few key points here. One that I already mentioned, this notion of goal-oriented metrics and incremental investments. One of the challenges in research is often to create a sense of urgency among researchers and motivate them to be very focused. And if any of you are graduate students trying to work on your PhD or your dissertation, you may have sometimes a similar feeling of pressure from your advisor, or if you're married like I was in graduate school, from your spouse. Even though I would often say you cannot schedule creativity, my wife did not believe that. She thought I could certainly schedule this and be done on a short timeline. But in this project, we really did have a short timeline and needed to be very focused and motivated. And so this use of goal-driven metrics and a process of doing error analysis on the problem, and then for each of those errors, identifying pieces of the system that might help improve those errors, and then doing headroom analysis to focus or to give us an estimate of the impact of solving those problems, allowed us to focus our investments and really drive the performance. We also leveraged something we call extreme collaboration, which very simply meant we put everybody, which at the end of the project was a team of about 20 researchers and engineers, in the same room, one big lab where we could all very actively collaborate and work on the technology. And we actually continue to use that model today. We still work in one big lab, a very open space that really has an amazing impact on the collaboration and the communication within the team. And then finally, this notion of disciplined engineering and evaluation, which, if you're dealing with anything that has to do with machine learning, is very critical, so that you're managing your data carefully, separating it into training data, development data, and blind test data. And we're always very careful to measure the system on blind test data, because if you don't have blind data, you really don't have any idea of how well the technology is working. So with all of that and a period of really just about 4 years, we were able to advance the performance of the system from that baseline all the way up through into that winner's cloud, which ultimately led us to this public event in 2011, almost 2 years ago now, with the final result here, where Watson ended up being victorious over Ken Jennings and Brad Rutter, the two best Jeopardy players in the world. And one thing I think that is kind of cute about this, I don't know if you can read it, but Ken Jennings, at the end, realizing that Watson had won, not only wrote his final answer, but also said, "I, for one, welcome our new computer overlords." So at least he had a sense of humor about it, which I appreciated. Now, of course, Jeopardy was a great way to drive and demonstrate the technology, but what we're really interested in is how we apply this to solve real interesting problems, business problems, for instance. And so there's a wide range of topics that we could explore, but on the research team, we've decided to focus, at least initially, on the healthcare space, and how do we adapt this technology to help physicians in doing things like diagnosis and treatment. So moving from this Jeopardy paradigm to a more general problem-solving paradigm has a few implications, and there actually are 4 areas that we need to change the way that the system works. The first one is the problem statement. So now, instead of a very simple, precise question as input to the system, we have a much richer, more complex problem statement, which in the medical domain is often, what are all of the symptoms, test results, lab results, the whole family history or medical history of the patient. This is all input now. In fact, it could be the entire electronic health record associated with that patient for the problem we're trying to solve. I mean, the question might still be fairly simply, what diagnosis explains this current set of symptoms, and then what treatment should I use to get the most effective cure for this disease? But the input is now much richer and complex. So the technology has to evolve to analyze that rich input and deal with it. The second challenge here is the interaction model. So Jeopardy is fairly artificial and constrained, but in a real application of the technology, we want it to be much more interactive and be able to explain the results that it's getting. So there's really two elements to that. So one, in terms of interaction, is the ability to capture feedback from the user. And again, earlier today we were talking about research on active learning to improve search results. A similar idea here is where can we interact with the user in an intuitive and natural way to capture feedback and make the system smarter over time. The third piece here related to that is how do we explain to the user the results that the system came up with. And it's not sufficient to just give a single answer, maybe with a number associated with it, but rather we need to give an intuitive explanation for that answer and how Watson came to that. And again, the approach here is to solve these problems by finding relevant evidence from the literature, so the explanation should give us easy access to the literature so that the human can see the explanation, the reasoning, the provenance for the answer. And then finally, this notion of learning, so after we've captured feedback from the user, how do we incorporate that into a continuous learning process? So now when we look at the medical domain, the terminology is quite different than in open domain question answering. And so, here are some examples of just some of the problems that you run into. Let me just pick one here. So in the upper left corner, something like chronology. When we talk about the sudden onset of chills, it's important to recognize that sudden is a statement about chronology, and that maybe yesterday there were no chills and then today it was very sudden. And so understanding the chronology of that aspect of the language is important for how you interpret it. The lower right one about location, a very important aspect of dealing with health or medical literature, especially when somebody is describing their symptoms. If they're characterizing kidney pain, we need to know that the kidney is in the lower back, and that can be synonymous with lower back pain or flank pain or between the upper abdomen and the back, all similar expressions of location. One other common problem to deal with that I don't have represented on this chart is negation. So if in an electronic health record, the physician writes up a clinical note that says the patient does not have a fever or aches or pains, and we don't recognize that negation, we may misinterpret the meaning of that, and it can be very challenging. Matching between different words and phrases that ultimately mean the same thing really is at the heart of the problem here. And here are some examples of challenging matching problems. And so this first one here is we're looking for a neurological condition that contraindicates the use of bupropion. The word contraindicates means the same thing as should not use. But if we haven't explicitly programmed that into the computer doesn't know that. And so we need to come up with techniques that allow us to generalize this notion of knowing that should not use means the same thing as contraindicates. The second example says that the most common first manifestation of something. The text may not refer to it as first manifestation, it might refer to it as most common presenting symptom. Again, those two things are synonymous. The next two get even more subtle and complicated. The question is asking for a dietary indiscretion. There's a passage that talks about the correct answer, but it refers to a low-salt diet. And the connection to be made there is that a diet high in salt or sodium would be a dietary indiscretion. And so how do you even know how those two things are connected? And then this last one is too complex for me to remember how to explain it, so I'm just going to skip it. So now, how do we go about, again, driving the development of this technology? We actually started with a set of questions from the medical domain that have very similar characteristics to where we had just come from, which is Jeopardy. There's a collection of questions that are used to quiz medical interns in the United States called Doctor's Dilemma questions, and you can see some examples of those here. So they're phrased in a Jeopardy style, but they're obviously about medical questions and medical domain. So we started with those, and you can see the progression of the performance with different steps in the overall adaptation. So we have the baseline system at the bottom there, the original Jeopardy system out of the box running on these questions from the medical domain. And then there are three aspects to adaptation. First is content. So now rather than just using generic encyclopedic knowledge, let's apply some more specific medical content to that. The next one is to adapt the training data to be specific to the domain. And then the third, and really the most challenging piece beyond that, is functional adaptation, or what do we need to do to adapt the algorithms and the analytics to deal with the language from the domain, in this case, the medical domain. And so as we've progressed through those different steps, you can see how the performance has improved over time. So now, Doctor's Dilemma questions start to address how you adapt the technology into the medical domain, but they're not really representative of these rich problems that I was talking about. However, there's another set of questions in the United States called the United States Medical Licensing Exam. So now this is an exam that medical students would take at different points in their medical school career to eventually become licensed physicians. And these questions actually are a great way to test and evaluate the system. And so here's a couple examples of now these questions that tend to be much more complex. They provide a lot more background information and are going to be more challenging to answer. So how do we go about solving those kinds of questions? It turns out that with such a rich description, the first thing we need to do is be able to analyze it to extract out the most relevant factors. Beyond that, though, it turns out that these factors do not necessarily get you directly to the correct answer. Instead, we need to understand a number of intermediate connections and find intermediate relationships, intermediate pieces of information. So here's an example of trying to discover these paths that take us from some of the input problems, the input factors here. So at the bottom, we have something like the patient's hemoglobin concentration is 9 grams per deciliter, which is low. That implies that the patient has anemia. So that was not explicit. That's one of these inferred factors, which then implies that the patient has normocytic anemia, which ultimately implies that the most likely cause of this low hemoglobin concentration is erythropoietin deficiency. And so to get from these input factors, there's this process of generating intermediate results and then reasoning over them to propagate some confidence up to the final answers. And moreover, along the way, we want to justify each of these steps by analyzing the literature. So here you see snippets from passages that would justify that process of going along these paths from the factors to the final results. Now, this whole approach actually is motivated by the way humans solve these problems. So here's that same problem and a solving or a diagram that a medical student that we had hired to work with us produced as an example of how they would go about solving this problem. So this whole approach of creating paths from input factors via relationships that are justified with evidence from the supporting literature to get us to the final correct answer is motivated by sort of the human reasoning process that we use here. And that leads us to the next evolution of the Watson technology that we call Watson paths. And so now this goes beyond simple question answering to analyze the input problem statement represented in the upper left there to create the most relevant factors, which you see diagrammed across the top. So that's the input factors. Along the bottom, in this case, the question happens to be multiple choice, so we know what the hypotheses that we want to consider are. We can also automatically generate these hypotheses, or in an application where a human wants to do hypothesis testing on their own, they can provide their own hypotheses. And then the task is to make connections from the input factors to the hypotheses and identify the most likely correct answer. So in the first round, Watson Paths uses the underlying Watson question answering system to automatically generate sub-questions. and create or identify potential intermediate factors and create relationships from the input factors to those intermediate factors, and start to build out this graph that connects from the input to the output. And then ultimately all of these paths are supported by references from the literature. So you have this notion of automatic question generation under the covers to create these intermediate factors, relationships that connect them together, and then for each of those factors, a confidence in that factor that can be propagated through the network using a Bayesian inference style propagation to have all of these probabilities sort of settle in the most likely final answer here. And so this is a simplified representation. Here's a raw graph that the system might produce automatically. What I was showing you before was sort of a filtered view of that, highlighting just the most relevant pieces. A key to this, as I mentioned, is access to the supporting evidence that was used to build out these paths along the way. So if we zoom in on that dark blue edge, for instance, and we want to understand what evidence supports going from Parkinson's disease to substantia nigra there, we can drill down and look at the question, or actually it was the previous link that connects that input factor to Parkinson's disease. So now you can see some of the evidence that was used, and we can drill down into that and open up the document that contains the actual passage that justifies that edge. So now imagine in the graph, if you want to understand why these input factors lead you to the final conclusion, you can easily navigate through this to see the literature that was used to support that. So now there are a couple other elements to this that I just want to mention briefly and then wrap up. And these elements have more to do with this learning capability, something that we sort of generally call Teach Watson, and looking for opportunities to dialogue with the user and capture feedback that can make the system smarter along the way. And so back to that problem I was talking about earlier about what neurological condition contraindicates the use of bupropion. If the system is considering seizure disorder as a possible answer to that question, but has the passage on the right there, patients with pre-existing seizure disorder should not use bupropion, again, in order to use that passage as evidence to support seizure disorder, we have to know that should not use means the same thing as contraindicates. At this point in time, if Watson doesn't know that, it can actually detect the ambiguity and rephrase that or repose that as a question to the human and say, does should not use bupropion mean contraindicates the use of bupropion? And even more generally, does should not use mean contraindicates the use of in general? So there's, within the system, the ability to recognize these ambiguous situations and generate questions to help clarify them. There's several versions of this. That previous one was about learning synonyms and paraphrases. There's a version for learning entailments. So if you want to know that narrowing actually entails obstructing, we can have Watson do a similar kind of analysis and then ask the question, does a gallstone obstructs the common bile duct mean narrowing of the bile duct by a gallstone? So again, the entailment here is that if something is obstructing it, it is narrowing it, and we need to be able to learn that. There's a notion of learning types. So if we're looking for thienopyridine derivative that reduces the incidence of MI, blah, 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 and we want to know if clopidogrel is an instance of one of these thiopyridine derivatives. This is an instance of learning these types and getting some clarity on that. And then finally, here's an example of the system interacting with the end user to actually ask for missing factors. And so we have an example of a patient coming in with some symptoms, red painful eye, blurred vision, a family history of arthritis. And the question is, what diagnosis explains this patient's condition? Well, based on the factors that were originally given, these symptoms, Watson can come up with this initial ordering of diagnoses, starting with Behçet's disease as the most likely diagnosis. When analyzing the passages that support these other possibilities, however, Watson notices that Lyme disease is often associated with circular rash, fatigue, and headache, but those weren't discussed at all, and can pose a question back to the user to say, do these symptoms exist, and should they have been considered in the diagnosis? And the user can then say, oh, well, in fact, yes, there is circular rash and there is fatigue, and then that changes Watson's confidence in Lyme disease as the most likely diagnosis for this situation. So what I've done is hopefully given you an introduction to the Watson technology, sort of motivated this notion of a Jeopardy Grand Challenge as a way to drive the technology and demonstrate it in a very, I think, public and exciting and interesting way. And then giving you a very quick introduction to how we're starting to adapt this technology to solve a real business problem in the medical domain, and how the next generation of the technology is this Watson Paths approach that can deal with much more complex inputs, and then starts to add this notion of sub-questions, intermediate factors, and reasoning over that to ultimately solve much more difficult and challenging problems. Thank you. Yes.
Yes, Watson goes to the area of natural language or natural thinking in a way. I wonder if the machine can already think. How do you, what is your idea if would Watson pass the Turing test already?
Okay, so this is a question from one of my IBM colleagues who wants to know if Watson can already think and pass the Turing test. So it's an interesting question. I think our approach to developing the technology so far has not been to try and model the way that the human brain works. And again, I met earlier with some people that were working more on sort of the boundary between neuroscience and computer science, and looking for ways to understand how the human brain works. Some of this is motivated by the way humans do understand natural language. Certainly, we've created formalisms for parsing language and understanding syntax and grammar, and we're able to codify that. But ultimately, I think internally, Watson is solving these problems in a slightly different way. And at this point, I don't necessarily characterize it as thinking. I characterize it as sort of the application of a wide variety of analytics, which range from fairly deep, like our deep parser, which does a pretty good job of understanding sentence syntax and parts of speech, to a variety of shallow techniques that can consider a whole bunch of different factors and features. And the key there is this machine learning approach to learn automatically how to weigh and combine the results of all these different analytics. Yes, here. Right, so what kind of processing power do we have driving the Jeopardy version? So for the Jeopardy demonstration, which was now, as I said, over 2 years ago, to achieve the speed requirements, we used 90 IBM Power 750 servers. And that was what the total hardware cluster had in it. I think we actually only ran on about 75 or 80 of those. We had a few saved as backup. But the total processing power of that whole cluster included, each server had 32 cores in it. So I think that gave us 2,880 cores, where each one of these cores is, a fairly powerful processor in and of itself. It's something like a 5 gigahertz system. We had a total of, I think, about 15 terabytes of main memory. Again, one of our approaches to getting the speed was to avoid any disk I/O with the data, and so we had enough main memory to keep everything cached in main memory. And that sounds like a lot of processing power, and it is, but when you think about how, again, your favorite web search engine goes about delivering the kind of performance that you see in your web search, they're doing the same kind of thing. They're keeping things cached in main memory. It's behind the scenes. They're using hundreds of thousands of servers here. Now, the good news is that over the last 2 years, IBM has actually invested a lot to sort of scale down the footprint. This was a software system originally developed by a research team, which, yes, we tried to be disciplined in our software engineering and code efficient algorithms, but ultimately, there's probably people that can do even better at making things faster, and so that's what IBM has done in the meantime. And I believe that the whole system now actually runs almost as fast in a single one of these Power 750 servers instead of the 75 or 80 that we used. Yes, here. So have we tried other languages? So there's huge interest in applying this technology to other natural languages. So far, we've only done work on Watson in English. Within IBM in general, there's a lot of work on other languages, either from a machine translation approach or also from native natural language processing techniques for those different languages. And but this is something that we'll start to explore in the very near future. Yes, in the back. So what are IBM's plans for selling Watson? About 18 months ago, we created a new commercial division called the Watson Solutions Division, which is tasked with commercializing the technology and looking for opportunities to work with clients to apply the technology to solve their problems. And to date, I think we've announced a couple of engagements with partners, mainly in the healthcare space. And so we've been using it to support in one instance, working with Memorial Sloan Kettering Cancer Center in New York to create an oncology advisor that can help physicians ensure that they're applying the most current best practices and guidelines for treating patients. And so this is one of the early solutions that we've been working with in partnership with Memorial Sloan Kettering. And so that's where some of the first commercial activity has been. Yes? Like the onion. Let's see. So the question is, can Watson detect sarcasm? I don't know that we looked at sarcasm specifically. So again, in Jeopardy, this tends to be a fairly narrow and specific requirement to deal with things like puns. And so we did have to add some additional capability to understand puns. And so what's a pun? Typically, you would have a question where there's a word in quotes. And so, for instance, there was one clue that was something like there's a college and seminary in this holy Minnesota city. And so holy was in quotes. So holy Minnesota City is actually a pun, and the way that we can leverage that is if we're given a choice between a couple of different Minnesota cities like Minneapolis or St. Paul, which of those two cities is more holy? And so there you could use that pun information to prefer St. Paul as the correct answer versus Minneapolis. So we've done a little bit of work there, but that tended to be very specific to Jeopardy. The challenges now are more about dealing with language and the terminology, the vocabulary that tends to be specific to these different business domains. The medical domain has all sorts of challenges associated with understanding the terminology and, again, knowing when two words or phrases mean the same thing, when they mean the opposite, when they are inconsistent. And so these are sort of the interesting problems that we're working on now. Yes?
How much of Watson's success do you think is thanks to
Well, so the question is, how much of the success is due to the quality of the sources? So there's a couple levels to that. So in order to answer any question, the answer has to be in your corpus, and it can't just appear in the corpus, it has to be in the corpus in a way, in a context that supports it as the correct answer to the question. Early on in the project, actually, identifying all the relevant content that we would need in order to answer a broad and large enough set of Jeopardy questions was a big element of that. Related to that, one side comment I should mention is that when the system competed on Jeopardy, it was completely self-contained. So we had to identify all the content we were going to use ahead of time. It did not have a connection to the internet. And what we discovered, though, was that after about 18 months of doing content analysis, we actually had a big enough corpus that we didn't need to look at that a whole lot more. We had sort of assembled enough that everything that we needed to address the challenge. The quality question, I mean, there's a number, I guess there's different ways to measure quality. I mean, first it has to be accurate and authoritative, and that actually becomes very important in some of these business applications like the medical domain. And so we're very careful about understanding the authoritativeness of the sources. But then the other is sort of how easy is it for the text analytics to process that content? So is it well written? Is it grammatically correct? And so it certainly helps if the content is well written. But it doesn't have to be. I mean, these techniques do tend to be fairly robust even as the quality degrades. And so it really comes down to how well it justifies the answer in the context of the question. Yes? Okay, so the question is, could you use this technology to compare two different sources, roughly speaking? That's a good question. I think that if you look under the covers and at all of the different analytics in the system, there's a lot there that you could use to start to look at that kind of comparison. But off the shelf, I'm not sure that it would solve that problem for you exactly the way it is. But to the extent that you wanted to identify features in the text that are useful in making that comparison and that analysis, I think there's a lot of sort of the building blocks within the technology that would let you do that. But off the shelf, it wouldn't do that for you right immediately. One final question.
Have you looked at the Watson with the medical record? Does it make any discoveries? Do you have a kind of a no answer, none of these, and then you would figure out this must be an
So when applying Watson to the medical domain, is it possible to discover new insights or perhaps some gap in the current medical knowledge? Well, it's certainly true that the way that the technology works based on computing a confidence in its answers, we can know when the system has not come up with any high confidence answer. And then we can further do some analysis to understand why that's the case. And so, either there's no supporting evidence in the content for a good answer, but in terms of sort of formalizing this notion of discovery, it's something that we haven't really started to look at yet. Okay. Thank you.